Okay, good morning, one and all. In today's session, I'm going to discuss about the stresses in composite sections. So, composite sections means two or more different materials, two or more bars of different materials, when connected together rigidly, they act as a single member. So, the stresses will be different in the materials as their Young's moduli are different, the length being same and the members being connected rigidly, the extension or compression under the external load will be the same. Under the tensile load, the extension of both the materials, both the bars will be the same because they are rigidly connected. Under compressive load, the decrease in length also is same in both the bars. That is, the strain is same. The length being same and change in length also being same, the strain will be the same in both the materials, both the bars. That is one condition in analyzing or solving the problems of composite bars. And second condition is the total load, external load that is applied is shared among the bars. If there are two bars, the total load is shared by the two bars. If there are three members connected rigidly, then the total load is shared among the three members. Okay? So, let us consider first the first conclusion here in composite bars. The extension or compression in each bar is equal. Hence, the deformation per unit length, that is the strain in each bar is equal. And the second condition is the total external load on the composite bar is equal to the sum of the loads carried by each different material in the composite member. So, using these two conditions, the problems of composite bars are solved. Okay? So, if P is the total load, L is the length of composite bar, and also the length of each bar of each member of the composite bar. A1, A2 are the cross-sectional areas of the two members which are connected rigidly. E1, E2 are the Young's moduli of the two members. P1 and P2 are the loads shared by each of these two members. And sigma 1, sigma 2 are the stresses induced in these two members. Okay? With this notation, we see that now the total load on the composite bar is equal to the sum of the loads carried by each bar, where P is the total load. Okay? P is the total load applied on the composite member. So, this is material 1, material 2 say. Okay? So, if P is the total load, then P1, P2 are the loads carried by the two different materials. So, the total load is equal to the sum of the two loads P1 and P2 carried by each of these two members. And stress in the material 1 or bar 1 is sigma 1, which is given as load carried by member 1 divided by area of cross section for member 1. Similarly, our P1 is equal to sigma 1 A1 from this. Similarly, we have sigma 2. The stress in member 2 is P2 by A2, or P2 is sigma 2 into A2. Stress in member 2 multiplied by cross-sectional area of member 2. So the total load is now given as P1 plus P2 actually, where P1 is sigma 1 A1 and P2 is sigma 2 A2. Okay. So we have this condition, one equation here, and the relation between sigma 1 and sigma 2 is obtained by equating the strains. So here the members are rigidly connected. So the extension or contraction is same. That is, the strain will be the same. The length of the member being same. Length of each member being same. Okay. The strain in bar 1, E1, is equal to stress by Young's modulus, sigma 1 by E1, and strain in bar 2 is equal to sigma 2 by E2. And we have the condition E1 is equal to E2. That is, sigma 1 by E1 is equal to sigma 2 by E2, or sigma 1 is equal to E1 by E2 into sigma 2. And this ratio E1 by E2 is called the modular ratio. The ratio of Young's moduli of two different materials. Okay, and which is known. E1 and E2 are the Young's moduli, the material properties. They are known. So we can find the modular ratio, and this equation gives the relation between sigma 1 and sigma 2. Okay, sigma 1 and sigma 2, and using this relation and substituting this in equation 1 here, sigma 1 and sigma 2 here, you can replace sigma 1 in terms of sigma 2 or sigma 2 in terms of sigma 1 and find out what is sigma 1 and sigma 2, because the areas are known and the load applied is also known. Areas A1, A2 are known. Okay, the cross section areas. So we can calculate sigma 1 and sigma 2, the stresses in members 1 and 2, and hence the loads P1 and P2 also. Okay, how will you get P1 and P2? Knowing sigma 1, you will get P1 as sigma 1 A1 and also P2 as sigma 2 A2. So you can find the loads carried by each of the member, and also the extension. You can calculate extension by calculating the strain sigma 1 by E1. You can calculate the extension of the composite bar. Okay. So this is how we solve the problems of composite members. And let us see some examples. First example, a steel rod of 3 centimeters diameter is enclosed centrally in a hollow copper tube of external diameter 5 centimeters and internal diameter 4 centimeters. The composite bar is then subjected to an axial pull of 45 kilonewtons or 45,000 newtons. If the length of each bar is equal to 15 centimeters, determine the stresses in the rod and tube and load carried by each bar, that is steel bar and copper tube. The Young's moduli are given. Of steel, it is 2.1 into 10 power 5 Newton per mm square. And copper, 1.1 into 10 power 5 Newton per mm square. So you can find out the modular ratio ES by EC, knowing the values of Young's moduli. Okay. Now, the lengths of steel rod and copper tube. The length is same for both. So the strain will be same. Strain will be the same because the extension or change in length, say decrease in length, is same for composite bar of same length. Okay. So the strain is same in both the materials, steel rod and as well as copper tube. The strain is same. Okay. Extension is same. Okay. These are the conclusions what we have seen. Okay. The total external load is equal to the load, sum of the loads carried by each of the materials, two different materials. Okay. And here diameter of rod is given 3 centimeters steel rod, which is fixed in copper tube of 4 centimeters internal diameter and 5 centimeters external diameter. Okay. So the cross sectional area of steel tube is pi d square by 4, where the diameter is 3 centimeters. And cross sectional area of copper tube, this is pi d square by 4. Diameter is 30 mm. And for copper tube, the area is pi by 4 into do square minus di square. That is outer diameter and inner diameter. dy is outer diameter and di is inner diameter. So that gives the area, cross sectional area of the copper tube. Okay. So area of copper tube also is 706.86. Okay. And that of steel rod is also same, 706. Okay. This is D is here 3. And dy is 5. And di is 4. 5 square minus 4 square is 3 square. Okay. That is pi by 4 3 square. So these two areas are equal. In this particular case, the area of rod and area of tube are equal. 5, 4 and 3 being the Pythagorean triplet. Okay. And axial pull applied is 45 kilonewtons. Length of each member is 15 centimeters. Young's moduli are given. So you find out the relation between stresses in members, stresses in steel tube, steel rod and copper tube. Stresses in steel rod and copper tube. You can find the relation. How? By equating the strains. By equating the strains in the two members. Strain in steel tube is given as sigma s by es, and strain in copper tube, strain in steel rod and strain in copper tube are equated. And sigma s is es by ec into sigma c. Es by ec modular ratio 2.1 into 10 power 5 by 1.1 into 10 power 5, which is 1.909. Okay, the modular ratio is 1.909. And this relation between the stresses is used in the other equation given by this. Load taken by steel rod and copper tube is equal to the total load 45,000 newtons. So PS plus PC is 45,000, where PS is sigma S AS, stress multiplied by area, cross-sectional area. And PC is also stress in copper tube multiplied by cross-sectional area. So, in place of sigma S, we substitute 1.909 sigma C and AS sigma C AC. So this gives stress in copper tube as 21.88 and stress in steel rod is 1.909 into 21.88, that is 41.77 Newton per mm square. Okay, and the loads PS, and we can find out the loads PS as sigma S AS and PC as sigma C AC. Sigma C AC. Okay, so 41.77 into AS is 706.86. So this gives in newtons multiplied by 10 power minus 3 in kilonewtons. Similarly here 21.88 sigma C into 706.86 into 10 power minus 3. So this gives the loads shared by steel rod and copper tube. Okay, yeah, for composite members of equal length, for composite member in which the different members are of same length, then we can proceed in this manner. Okay, now let us see another example. A concrete column, reinforced concrete column, also can be treated as a composite member only, consisting of concrete and steel. A concrete column reinforced with steel bars is treated as composite member. Okay, so steel rods provided in concrete, reinforced in concrete. So this is concrete, reinforced concrete. Okay, so reinforced concrete column of cross-sectional area 400 mm by 400 mm, that means a square column, is reinforced with 4 round bars, one at each corner, of diameter 50 mm. Okay, these are steel rods of 50 mm dia, 50 mm dia, one at each corner. If the column carries a comprehensive load of 300 kilonewtons, determine the loads carried by concrete and steel and the stresses in steel and concrete. Take Young's modulus of steel is 15 times that of concrete. Young's modulus of steel is 15 times the Young's modulus of concrete. It means the modular ratio M is 50. M is 50. So in this case, the area of cross section of the column, gross sectional area is 400 into 400 here. Okay, area of cross section of the column, entire column including steel, that is 16 into 10 power 4 mm square. In that area of steel is, which consists of 450 dia bars. So the area of steel is obtained as 7857.14 square. That is 4 into pi by 4 d square. Okay. Area of 1 bar is pi by 4 into d square. So area of 4 bars is this much, 7857.14 square. And gross sectional area, gross area of the column is, which includes steel, okay, 16 into 10 power 4 square. Okay. So area of concrete is gross area minus area of steel. That gives area of concrete as 152,142.86 square. Okay. So the condition here is same. The strain is equal in concrete and steel, and the load is shared among the members. Okay, that means load carried by concrete plus load carried by steel equal to the total load applied. The total load applied, compressive load, is 300 kilonewtons or 3 lakh newtons. Okay. So the axial pull, it is not 45, it is 3000 newtons, and let L be the column length. So the axial load is 300 kilonewtons, actually 300 kilonewtons. The load on the column is 300 kilonewton, that is 3 lakh newtons. Okay. So now equating strains, strain in steel and strain in concrete. This is concrete. Strain in steel is equal to strain in concrete. That is sigma S by ES equal to sigma C by EC. Okay. Sigma S is equal to ES by EC into sigma C. And this ratio ES by EC is given, the modular ratio is given as 15. Okay. And we use this relation in this expression. Okay. The total load is equal to sum of the loads carried by steel and concrete. That is sigma S AS plus sigma C AC equal to 3 lakh newtons. And replacing sigma S by 15 sigma C. Okay. We get the stress in steel as 1.11 Newton per mm square. Okay. Sorry, stress in concrete. This is sigma C. Stress in concrete is 1.11 Newton per mm square. And stress in steel is 15 times of sigma C. 15 times of sigma C. That is 16.67 Newton per mm square. Okay. Now load carried by steel rods is sigma S into ES. AS, sigma S into AS, that is area of steel rods, and this is sigma C into AC. Sigma C into area of concrete, this one. Okay. And sigma S into area of steel is this one. So this gives load carried by steel rods and load carried by concrete column. Okay. So with this, I conclude this session. Thank you. Let us discuss some more examples in the next session.
Like, share and subscribe. Hit the bell icon for more updates.